currents measured in the loop? They're all wrong.
Of course they are.
How many currents are in the loop?
Depending on how you see it, could be one or several.
If you're going to learn physics, you're going to have to learn the rules.
The good cop, bad cop routine?
Not exactly.
Never start with the abstract concept. The student gets all fuzzy. They can't understand the next... See?
You wanted physics. Here I am.
I wanted to understand how current works, and you didn't disappoint. You simplified multi-loop circuits by adding additional rules and concepts for students to learn. Even to a guy like me, that's cold.
What's the value of the unknown resistor?
Those simple single-loop circuits were easy to break down and understand, but it's not that easy when you throw in Kirchhoff's laws. But I know the truth. There is no going back. You've changed things. Forever.
Then why do you want to ignore me?
I don't want to ignore you. How could I ever solve the unknown resistor for the Wheatstone Bridge experiment without you? You complete me.
Hello everyone, today we are going to use a special circuit called a Wheatstone Bridge to find the value of the anode resistor. This is the diagram of the circuit. The Wheatstone Bridge is a circuit used to measure an anode electrical resistance by balancing two sides of a bridge circuit. And our hypothesis is that by carefully adjusting the node resistances in the bridge, we can balance the circuit and calculate the value of the anode resistor. So let's get started. To do this experiment, we'll need a few things. First, we need Wheatstone Bridge circuit. This is the main tool we'll use. It's like a special circuit that helps us balance the electric flow. And we need power supply. This is like a battery. It gives the circuit the energy it needs to work. And we need ammeter. This is a tool that measures the electric current flowing through the circuit. It tells us how much electricity is moving. And we need voltmeter. This tool measures the voltage. And of course, we need resistors. These resistors slow down the electric current. We'll use resistors that we know the value of and one that we don't know the value of. And lastly, we need connecting wires. These wires connect all the parts of the circuit together.
Now that our circuit is set up, we are ready to start the experiment. We'll begin by adjusting the known resistors on the bridge using the decay box. By carefully adjusting these resistors, we are trying to balance the bridge. When the bridge is balanced, the current flowing through the ammeter will be zero. This means that the ratio of the resistance on one side of the bridge is equal to the ratio of the resistance on the other side. As we adjust the resistors, we'll keep a close eye on the ammeter. When the value on the ammeter reaches zero, we will know that the bridge is balanced. At this point, we can use the known values of the resistors to calculate the value of the unknown resistor. We'll repeat the process several times, adjusting the resistors each time to get an accurate reading. We will also record the values of the known resistors and the corresponding readings on the voltmeter. This data will help us verify our calculations and ensure the accuracy of our results. So to find the value of the anode resistors, we will be using the Kirchhoff law. There are two laws we will be using for this experiment. The first one is the Kirchhoff current law, which means that the sum of the current entering the node is equal to the sum of the current leaving the node. The second one is called the Kirchhoff voltage law, which means that all the voltages around the closed loop is equal to zero, because the circuit is a closed conducting loop and there is no energy loss. Now again, let's look at the diagram. From point A, we have two currents coming up. Let's say they are I1 and I2. So in the first part ABCA, using the Kirchhoff voltage law, we can say that I2R1 is equal to I1Rx. Again, in the second part BDCB, we get the equation I2R3 is equal to I1R2. So when we write both equations to simplify, we finally get Rx is equal to R1, R2 by R3. In our case, R1 is equal to 2000 and R3 is equal to 1000. Plugging in those values and the other resistors, we get the value of the unknown resistors. So how do we calculate the error percentage in each case? For that, we can use this formula. Plug in the values and then we get the error percent. To calculate the propagated error in our experiment, we are going to use a formula that includes the uncertainty in our measurements. This formula is derived from the equation for a balanced Wheatstone bridge we got earlier, Rx equal to R1, R2 by R3. By rearranging this equation, we get the formula shown to calculate the uncertainty in Rx. So the first term of the equation accounts for the uncertainties in R1 and R2. It shows how changes in R1 and R2 affect the value of Rx. The second term accounts for the uncertainty in R3. It shows how changes in R3 affects Rx. Now we can substitute the values from our experiment into the formula. We know the values of R1, R2, R3 and their respective uncertainties. By plugging these values into the formula, we can calculate the propagated error in Rx. In our case, the calculated propagated error in Rx is 88 ohms. It means that our calculated value of Rx could be off by as much as 88 ohms due to the uncertainties in our measurements.
After conducting multiple trials and recording the data, we can now analyze our results. By analyzing the data, we can see that the errors percent is not very high, which means that we could successfully determine the value of the unknown resistor. However, there may be some sources of error that could have affected our results. For example, the precision of the resistors and the accuracy of the meters could have introduced small errors. Now let's see the next question, which is better between ammeter and voltmeter. An ammeter measures how much electricity is flowing. When the bridge is perfectly balanced, no electricity flows through the middle part of the bridge. So if we use an ammeter, we will be looking for a reading of 0. However, there are some problems with this. It can be hard to get a reading of exactly 0, especially if there is a bit of electrical noise in the circuit. Also, modern voltmeters are better at detecting very small changes in voltage, which can help us find the balance point more accurately. Here's a quick comparison of the two. Ammeters are simple, direct, but less sensitive. On the other hand, voltmeters are more sensitive, precise, and better for fine adjustments, though slightly more complex. While both can achieve the same goal, the voltmeter can give us better precision. So finally, in this experiment, we successfully used a Wheatstone bridge to determine the value of an unknown resistor. By carefully adjusting the known resistors, we are able to balance the bridge and calculate the unknown resistance. Our experimental results confirmed our hypothesis that the Wheatstone bridge can be used to accurately measure unknown resistances.